Here's one more example of how you might use the Nernst equation in a redox reaction calculation. This problem, we're told that we have a galvanic cell. When we see the word galvanic cell, we know that that means that we're going to have a positive E cell or positive E standard cell, because galvanic cells always produce voltage, so it's always a positive number. And we have the following unbalanced redox reaction in acidic solution. So telling us that the redox reaction is unbalanced, that's a hint that we're going to need to balance this reaction. We're given concentrations of VO2 plus, which is one of the components, and H plus, which is going to be in here somewhere, but we don't know where, so we are not going to be able to get away with not balancing it. And then we have 1.38 of VO2 plus and 4.09 molar Fe2 plus. Calculate the voltage of the cell. Okay, so we can totally do this. The first thing that I want to do is balance the equation. That's going to be my step one. We need to balance this thing. And you've learned how to balance these balanced redox reactions stepwise. I'm sure you're very, very good at it right now, and I'm probably going to break your heart by showing you a trick for avoiding balancing redox reactions if you don't want to actually balance them. And we're going to do that by going to our table of half reactions, and we're just going to find the reactions in this table, because in this table they are balanced already, and some of them are acidic and some of them are basic, but we're going to be able to pick out which is which. So I'm looking for the iron and iron 2 plus half reaction, and I can see that it is, we've got to be careful to find the right one. I can see it's right here. So in this, not only am I looking for the voltage, I kind of don't even need it right now, we're going to need it eventually. I'm also looking really closely at how this reaction is written. Now, this reaction may be written in the wrong order. We're going to have to check it when we go back to the overall balanced equation, but I'm paying attention to the other components and the stoichiometric coefficients in this equation, and I'm going to copy it based on how the reaction actually works in our reaction. So in our reaction, we have the iron solid on the left side. We have the iron 2 plus on the right side. That means that we need to have our 2 electrons on the right-hand side. And what was the voltage of that? The voltage of that was negative 0.447. Now that's not really saving us a ton of time, because you can balance that redox reaction really quickly. That's not that tricky. Let's look at our other ones. So now we're going to be looking for a VO2 plus and VO2 plus. Let's go find that one. So here it is down here. We have VO2 plus and we have VO2 plus. And is this an acidic solution? Yes, it is. So we can see we have H pluses without OH minuses present, so that means we're good to go. So look, it's already balanced for us. We're not going to have to go through the steps of balancing this half reaction. Wonderful. We need to copy exactly the way that it's written. We do want to make sure that we're getting the VO2 plus on the left, or on the correct side. Let's take a peek here. We want the VO2 plus on the left side. So we want this equation exactly as it's written. VO2 plus aqueous plus 2H plus aqueous plus 1 electron makes VO2 plus aqueous and H2O liquid. And the voltage for this was positive 0.991. So there are the half reactions. Now we are going to combine the two half reactions together. Before we do that, remember we've got to take a look at the electrons in the half reactions. Since we only have 1 electron in the vanadium reaction, we have to change the stoichiometric coefficient double the stoichiometric coefficient of everything in that reaction so that the electrons are going to cancel out. So I'm going through and doing that right now. And now we're going to combine the two reactions together. 2VO2 plus aqueous plus 4H plus aqueous plus Fe solid. I'm not going to write these electrons down because they're just going to cancel. And that makes Fe2 plus aqueous and 2VO2 plus aqueous and 2H2O liquid. And I hope you don't hate me for making you learn how to balance redox reactions when you can just look them up in a table. They're not always in the table, so you do still need to know how to do it. So we've got our balanced equation now. We're good to go, and we've dealt with the acidic solution part, and now we need to calculate the voltage of the cell. Calculating the voltage of the cell, because this is a non-standard cell, and we know that it's non-standard because we have these molarities that are not 1. So we need to use the Nernst equation, so let's get that set up. Set up our Nernst equation. And that is going to look like E non-standard cell equals E standard cell minus 0.0257 volts over N times the natural log of Q. And let's see what we can fit where into this equation. So we know the N, that's the number of electrons from the balanced redox reaction, that's 2. We can figure out Q. Q is going to be products over reactants raised to the coefficients. We're going to have Fe2 plus times VO2 plus squared, we're going to leave out water, over VO2 plus squared and H plus to the 4th. And we have concentrations for all 4 of these things. So we can get their concentrations from the problem and we can plug those in. First we have the iron, which is 4.09, and our VO2 plus, which is 1.38, and that one's going to be squared. Divide by the VO2 plus, that's 0.496. 0.496, and that also needs to get squared. And then our hydrogen concentration, 3.48, and that one is raised to the 4th. So there's that, and we can figure out what that is. Let's do the math on that really quick. 4.09 times 1.38 squared, divide by 0.496 squared, and divide by 3.48 to the 4th. So that works out to be 0.216. So the last thing that we have to figure out here is E cell. And because this is galvanic, we don't really need to think that much about the correct order. We're using our voltages of half reactions, and we just need to put them together in a way that's going to give us a positive voltage. So it looks like I want to do 0.991 minus negative 0.447. That's the only way that I'm going to get a positive number. And that voltage will be 1.438 volts. So now we have everything we need to actually solve this problem. Our non-standard E cell is 1.438 volts. We're going to be subtracting 0.0257 over 2, our N, times the natural log of Q, which is 0.216. So all we have to do now is just work the math out on this. I'm going to do the natural log part first. Natural log of 0.216 times 0.0257 divided by 2, and then 1.438 minus that number. And our non-standard voltage is 1.458 8 volts. Not a huge difference. There's our answer.